Hello friends, the topic of today's discussion is Jahn-Teller Distortion. In this, we will discuss the following points. What is Jahn-Teller Distortion? Jahn-Teller Distortion in octahedral complexes. Splitting up T2G and EG orbitals due to Jahn-Teller Distortion. Relation between d electron configuration and type of Jahn-Teller distortion, and finally some problems based on Jahn-Teller distortion and their solution. Jahn-Teller distortion is a geometric distortion of a nonlinear molecule to reduce its symmetry and energy. This distortion is typically observed in octahedral complexes. This can also be observed in tetrahedral complexes, but in this lecture we are going to discuss only Jahn-Teller distortion in octahedral complexes where it is more pronounced. Jahn-Teller distortion depends upon the electronic state of the system. Let's have the example of a hypothetical molecule Ml6. If it has a regular octahedral geometry, it can be drawn like this, where there are two types of metal ligand bonds, 2 axial and 4 equatorial. Let's denote the axial bonds by a letter A and equatorial bond by E. In a regular octahedral molecule, all the 6 bonds are of the same length, that is, A is equal to E. If we compress the axial ligands along the z-axis like this, called Z-in distortion, it would give this tetragonal structure, where A is shorter than E. Similarly, if we elongate the axial ligands along the z-axis like this, called Z-out distortion, it would give a tetragonal structure like this, where axial bonds are longer than equatorial. This tetragonal distortion from octahedral symmetry is called Jahn-Teller distortion in octahedral complexes. This occurs when the metal ion in the complex has unsymmetrical filling of T2G or EG orbitals. Complexes with unsymmetrically filled T2G orbitals show weak Jahn-Teller distortion, while complexes with unsymmetrically filled EG orbitals show a strong Jahn-Teller distortion. This distortion lowers the energy of the metal complexes, or we can say increase the stability of the complex. Whether the distortion is Z-in or Z-out depends upon which distortion is leading to more stabilization. Now, we will discuss the splitting up T2G and EG orbitals in tetragonal ligand environment due to Jahn-Teller distortion. This is the d orbital splitting diagram for a regular octahedral complex. In Z-out distortion, the two ligands on the z-axis move away from the central metal. In doing so, they reduce their interaction with the d orbitals that have z component, that is dz square and dxz and dyz. As a result, these orbitals are stabilized, means their energy is reduced. Because of center of gravity rule, the orbitals without z component, that is dx square minus y square and dxy, are destabilized, means their energy is raised. The difference between the energy of dx square y square and dz square is denoted by del 1, and that between dxy dxz and dyz is denoted by del 2. The energy of dx square minus y square is raised by half del 1, while the energy of dz square is lowered by half del 1. The energy of dxy is raised by 2 upon 3 del 2, while that of dxz dyz is lowered by 1 upon 3 del 2. The difference between the energy of dx square minus y square and dxy is equal to delta O. Similarly, in Z distortion, the two ligands on the z-axis move towards the central metal. In doing so, they increase their interaction with the d orbitals that have z component, that is dz square, dxz and dyz. As a result, these orbitals are destabilized, means their energy is raised. Because of center of gravity rule, the orbitals without z component, that is dx square minus y square and dxy, are stabilized, means their energy is reduced. The difference between the energy of dz square and dx square minus y square is denoted by del 1, and that between dxy dyz and dxy is denoted by del 2. The energy of dz square is raised by half del 1, while the energy of dx square minus y square is lowered by half del 2. The energy of dxz and dyz is raised by 1 upon 3 del 2, while that of dxy is lowered by 2 upon 3 del 2. The difference between the energy of dx square minus y square and dxy is equal to delta O. Here, delta O is far greater than del 1, which in turn is greater than del 2. Let's examine the Jahn-Teller distortion in octahedral complexes having d1 to d10 electrons in the metal ion with delta O less than pairing energy. Here, we can see that d3, d5, d8 and d10 have symmetrically filled d orbitals, so they will not show Jahn-Teller distortion. While d1, d2, d4, d6, d7 and d9 have unsymmetrically filled d orbitals, so they will show Jahn-Teller distortion. Among these, d1, d2, d6 and d7 with unsymmetrically filled d2g orbitals will show weak Jahn-Teller distortion, while d4 and d9 with unsymmetrically filled eg orbitals will show a strong Jahn-Teller distortion. Here, delta O is less than pairing energy, which is the high spin condition. So we can say that d6 and d7 high spin octahedral complexes show weak Jahn-Teller distortion, while D4 and D9 high spin complexes show a strong Jahn-Teller distortion. In octahedral complexes having D1 to D electrons in the metal ion with delta O greater than pairing energy, D3, D6, D8 and D10 have symmetrically filled d orbitals, so they will not show Jahn-Teller distortion, while D1, D2, D4, D5, D7 and D9 have unsymmetrically filled d orbitals, so they will show Jahn-Teller distortion. Among these, D1, D2, D4 and D5 with unsymmetrically filled T2G orbitals will show weak Jahn-Teller distortion, while D7 and D9 with unsymmetrically filled EG orbitals will show a strong Jahn-Teller distortion. Here, delta O is greater than pairing energy, which is the low spin condition. So we can say that D4 and D5 low spin octahedral complexes show weak Jahn-Teller distortion, while D7 and D9 low spin octahedral complexes show a strong Jahn-Teller distortion. Now we will discuss some problems based on Jahn-Teller distortion. Question number 1. Predict the nature of Jahn-Teller distortion in TiH2O6 3+. The oxidation state of titanium in this complex is +3. So the number of electrons in titanium 3+ will be 22 minus 3 is equal to 19. Since the number of electrons in the titanium metal is 22 and titanium 3+ will be formed by the removal of 3 electrons from it. To find out the electronic configuration of titanium 3+, write Ar3d. Ar has 18 electrons, so the remaining electrons that will enter the d orbitals will be 19 minus 18 is equal to 1. So this is D1 complex. Electronic configuration of titanium 3+ in octahedral environment will be T2G1 Eg0. Since it has unsymmetrically filled T2G, so it will have weak Jahn-Teller distortion. This is the crystal field splitting diagram showing splitting of d orbitals in regular octahedral environment along with their splitting during Z-in and Z-out distortion that we have discussed earlier. If the distortion is Z-out, the electron will be here. Under that situation, the CFSE due to Jahn-Teller distortion will be minus 1/3 del 2. If the distortion is Z-in, the d electron will be here. Under that situation, the CFSE due to Jahn-Teller distortion will be minus 2/3 del 2. This suggests that there is more stabilization in Z-in distortion. So the preferred Jahn-Teller distortion in titanium 3+ will be Z-in. Question number 2. Predict the nature of Jahn-Teller distortion in CuH2O6 2+. The oxidation state of copper in this complex is +2. So the number of electrons in copper 2 will be 29 minus 2 is equal to 27. Since the number of electrons in copper metal is 29 and copper 2 plus will be formed by the removal of 2 electrons from it. To find out the electronic configuration of copper 2, write Ar 3d. Ar has 18 electrons, so the remaining electrons that will enter the d orbitals will be 27 minus 18 is equal to 9. So this complex is D9 complex. Electronic configuration of copper 2 in octahedral environment will be T2G6 Eg3. Since it has unsymmetrically filled Eg orbitals, so it will have a strong Jahn-Teller distortion. This is the crystal field splitting diagram showing splitting of d orbitals in regular octahedral environment along with their splitting during Z-in and Z-out distortion. If the distortion is Z-out, the d electron distribution will be like this. Under that situation, the CFSC due to Jahn-Teller distortion will be minus 1 upon 2 del 1. If the distortion is Z-in, the electron distribution will be like this. Under that situation too, the CFSC due to Jahn-Teller distortion will be minus 1 upon 2 del 1. This suggests that we cannot predict Z-in or Z-out distortion based on CFSC in copper 2 octahedral complexes. The preferred Jahn-Teller distortion will be Z-out because it will have less repulsion between the ligand and the electron and the d electrons. Question number 3. Explain the reasons for the appearance of shoulder in the electronic spectrum of TiH2O6 3+. We know that TiH2O6 3+ is a D1 octahedral complex that undergoes a weak Z-in Jahn-Teller distortion. The d orbital splitting diagram due to Z-in distortion can be drawn like this. There is one d electron, so it will reside in dxy in the ground state. We can see that there are two possible transitions in the visible region of electromagnetic spectrum, dxy to dx square minus y square, transition A, and dxy to dz square, transition B. Transition B appears as the main peak and transition A at shoulder on slightly lower energy side. Question number 4. Classify the below complexes as having no, weak and a strong Jahn-Teller distortion. Let's take one by one. CO in thrice 2+. The oxidation number of cobalt in this complex is +2. So the number of electrons in cobalt 2 will be 27 minus 2 is equal to 25. Since the number of electrons in cobalt metal is 27 and cobalt 2 plus will be formed by the removal of 2 electrons. To find out the electronic configuration of cobalt 2 plus, write Ar 3d. Ar has 18 electrons, so the remaining electrons that will enter the d orbitals will be 25 minus 18 is equal to 7. So this complex is D7 complex. Ethylene diamine is a strong field ligand. The splitting of d orbitals and the electronic configuration of cobalt 2 plus in the octahedral environment will be like this. Since it has unsymmetrically filled Eg orbitals, so the Jahn-Teller distortion will be strong. FeCN6 4-. The oxidation number of Fe in this complex is +2. So the number of electrons in Fe2 plus will be 26 minus 2 is equal to 24. Since the number of electrons in Fe metal is 26 and Fe2 plus will be formed by the removal of 2 electrons. To find out the electronic configuration of Fe2, write Ar 3d. Ar has 18 electrons, so the remaining number of electrons that will enter the d orbitals will be 24 minus 18 is equal to 6. So this complex is D6 complex. Cn is a strong field ligand, so the splitting of d orbitals and electronic configuration of Fe2 plus in octahedral environment will be like this. Since it has symmetrically filled T2g orbitals and no electrons in EG orbital, so Jahn-Teller distortion will be no. FeCN6 3-. The oxidation number of Fe in this complex is +3. So the number of electrons in Fe3 plus will be 26 minus 3 is equal to 23. Since the number of electrons in Fe metal is 26 and Fe3 plus will be formed by the removal of 3 electrons from it. To find out the electronic configuration of Fe3 plus, write Ar 3d. Ar has 18 electrons, so the remaining electrons that will enter the d orbitals will be 23 minus 18 is equal to 5. So this is the example of D5 complex. Cn is a strong field ligand, so the splitting of d orbitals and electronic configuration of Fe3 plus in octahedral environment will be like this. Since it has unsymmetrically filled T2g orbitals, so Jahn-Teller distortion will be weak. CrF6 4-. The oxidation number of chromium in this complex is +2. So the number of electrons in chromium 2 plus will be 24 minus 2 is equal to 22. Since the number of electrons in the chromium metal is 24 and chromium 2 plus will be formed by the removal of 2 electrons from it. To find out the electronic configuration of chromium 2 plus, write Ar 3d. Ar has 18 electrons, so the remaining number of electrons that will enter the d orbitals will be 22 minus 18 is equal to 4. So this is the example of D4 complex. Fluoride is a weak field ligand, so the splitting of d orbitals and electronic configuration of chromium 2 in octahedral environment will be like this. Since it has unsymmetrically filled EG orbitals, so Jahn-Teller distortion will be strong.